Hello and welcome to fault locating on underground medium voltage power cables, part 2. Uh, in part 1, if you had gone ahead and attended or played that particular webinar, we covered the various fault locating techniques that are available to us today. We covered the capacitive discharge or thumping method, along with various forms of time domain reflectometry. Those included pulse echo, arc reflection, and impulse current reflection methodologies. In part 2, we're going to kind of move into a little bit of discussing and looking at cable faults and how we can go ahead and recognize different parameters, or what I like to refer to as profiling a cable fault, and then based upon the profile, select the appropriate test equipment and or strategy for successful locate on that fault. My name is Tom Sandry. I'm a Director of Technical Support here at ProTech Equipment Resources, and let's get moving along. First in our profiles of cable faults is one of the more straightforward type of cable failures that you will experience in your career. This is referred to as just an electrical tree or a pinhole in the insulating material of the underground cable. Now, the pinhole more than likely probably would have materialized through the natural aging process of water ingress and water treeing effects within the insulation. Again, if you remember from the webinar part 1, we discussed a little bit about bow tie and vented treeing in service-aged cabling. If we look at a pinhole fault from an electrical standpoint, basically what we would see is some nonlinear resistance value. If we were using like a megometer or something along those lines, we would be able to go ahead and measure the insulation resistance value or the remaining insulation resistance value on the cable. That would tell us basically what the resistance was. Now, keep in mind that an electrical tree is a void that has developed inside the insulating material of the cable. So the other parameter that we have is a gap, a physical void or gap between the conductor and the concentric neutral or shield of the cable. Now, the gap value, typically if we were doing a high potential test, we would go ahead and energize the cable. We would go ahead and apply some value of voltage, and if the cable was in good shape, healthy insulation, in essence what we should see is that the circuit is holding voltage, and we would see very little to no leakage current flowing back on the concentric neutral or the shield. If the gap value, however, breaks down, in essence can no longer support or sustain the voltage that we are applying to it, what we would observe on the high potential test set is a drop in the voltage value, and we would start to see a rise in leakage current. So when testing this type of cable fault, one of the things that we're looking for when profiling, we can use a simple megometer, measure the insulation resistance value. Again, the higher the insulation resistance value, the better the condition of the cable. We could also use a high potential test set. It could be either a DC or it could be very low frequency or VLF AC style. Again, if you are using DC high pots, please be a little bit cautious, particularly with service age cables, particularly those of the polyethylene, crosslink polyethylene type classes, because these particular type of cables are very prone to treeing effects, and research and studies by EPRI and various members of the Insulated Conductor Committee have definitely determined that DC testing on surface aged cables, particularly those prone to water treeing, the DC testing could actually cause more problems or future problems. So the gap value would be measured with the high potential test set. The insulation resistance value measured typically with a megometer. What we want to see is the cable supporting or holding the applied voltage and leakage current being at a very minimum. During a breakdown, as I stated before, we would see a drop in the voltage value, cable can no longer sustain, and we would start to see a rise in the amount of leakage current flowing through the fault. If we were using a capacitive discharge device and we were beginning to thump or surge onto the cable looking for breakdown, let me just clean up this screen here a little bit. Okay, so if we're using a surge generator, we're now applying breakdown voltage to the faulted cable. What we would typically see here is as we increase our output to the value that we want to discharge or thump at, when the instruments, the surge generator or thumper's discharge switch closes, what we should see is a rather sharp drop in the voltage and a rather strong kick forward on the amp meter, showing the inrush current at the arc flowing back on the concentric neutral. So again, another thing that we're looking for in this fault profile to let us know that conditions are good for our locate is when we are thumping, we should be able to see every time the surge generator discharges, we should be able to see a rather good, strong kick on both the DC voltmeter and the DC ammeter. Now, if we were looking at the electrical tree or the pinhole in the cable using one of the time domain reflectometry methods, for instance the pulse echo method, the value of the insulation resistance and the physical gap value may be much higher in impedance than the low voltage applied by the time domain reflectometer can actually see. So it's very common in this type of situation that if we were using the pulse echo or cable radar system all by itself without any type of a high voltage device, our captured pattern would show our transmitted pulse, the energy leaving the time domain reflectometer, and would more than likely just pass straight past the electrical tree or the fault. Again, the low voltage of the pulse echo device probably would not be able to detect or sense this impedance change, and what we would actually see is just a reflection off the farthest end of the cable where it is terminated in an open. Now, if we were using the arc reflection technique, what we would do here is we would first capture the low voltage waveform as I highlighted and illustrated in red, and then we would go ahead and turn on the surge generator. Once we would turn on the surge generator, we would go ahead and set up a appropriate voltage level to go ahead and surge into the cable with the intent of causing the cable fault to arc over. Now, when that arc appears at the fault, for that moment of time, the impedance of the cable at that point is effectively 0 ohms, well within the range of the pulse echo or the time domain reflectometer's ability to capture and display the event as a short circuit. So again, we discussed this in the cable fault part 1, but if we were running the arc reflection test, if you remember from the first of this series webinar, the first pattern is the low voltage pattern, and will show us the end of the cable. The second picture that we're going to take is going to be while we are discharging with the surge generator and creating breakdown, we are also sending pulse echo pulses with the intent of when the arc is present, the circuit at that moment of time is a short circuit and we capture the negative reflection corresponding with the arc that we drive on the cable through the thumping process. So again, the electrical tree is a rather common fault that you will find on many of your service age cables. Profiling this fault is fairly straightforward, and typically this type of fault will not give us too much difficulty in locating. As we move up a little bit more in complexity of cable faults, we have the open conductor, or sometimes referred to as the blowout. Now, in this situation, in essence, the cable may have taken a very high current surge, and literally that surge of energy had caused the conductor and possibly the neutral as well to completely blow apart. And in essence, what we have here is the cable now has been severed and is in two pieces. So it really now becomes a compound fault. As you see in my drawing, on end A, we're going to assume that end A is the source side of the circuit and B is the load side of the circuit. Now, you'll notice that I drew the gap on the source side of the circuit much larger than the gap on the load side of the circuit. The reason for this is, if you remember, when a cable fault fails, all of the fault current travels back toward the source along the path of the neutral or shield. Now, when a fault flashes over, the intensity of fault current, depending upon the magnitude of the fault, the voltage values at which it flashed over at, these fault currents can be several hundreds or thousands of amps. And in some situations, what will happen is this high fault current amperage traveling back will actually create what we call a burn back condition, where either the conductor burns back into the insulating material or the concentric neutral burns back. Bottom line, what happens is now the physical distance between the remaining conductor and that concentric neutral has grown in size, leaving a rather large gap. Now, chances are the load side of the circuit did not see this high intensity of fault current traveling back on its neutral. So from the load side of the circuit, the gap may be much smaller and more reasonable. Now, why is this important? If we're doing a high potential test and we're testing from the source side of the circuit, and also if the ground conditions are fairly dry, where we don't have a lot of creepage or leakage current flowing through the wet soil, when we run a high pot test, we actually may see, if testing from the source side, that the cable is capable of sustaining a rather large value of voltage before we start to see, any significant increase in our leakage current. It has also been noted on some occasions where when the ground is very dry, we have a blowout fault with a sizable burn back or gap on the source side. The cable may actually support and sustain the applied voltage during the test and not flash over. Now, if we are thumping onto the cable, another thing to watch for in the case of a possible burn back condition is when the thumper discharges, instead of getting a sharp kick or drop in volts and a strong kick forward in current, watch your meters. What may happen is you get just a very slight kickback on your voltmeter and just a very weak kick forward. This basically is telling you that the gap is very large. It's taking a lot of energy to drive that arc across it. Now, why do I make such a big deal of this? If you're having difficulty breaking down the cable fault, and particularly you're having difficulty getting good strong thumps or arcs established, listening for this fault when you go to do your pinpointing may be very, very difficult. If your thumper or surge generator is not breaking the cable fault over on every discharge cycle, again, that's an indication that this gap may be very large. Rather than fighting the problem, Most times it would be very beneficial if you have access to the other end of the cable or the load side of the circuit. Simply move the equipment, connect onto the load side of the circuit, and shoot back. Again, chances are on the low side of the circuit the gap may be much more reasonable and will allow you to get much better thumping conditions. Now, if we are looking at the blowout fault using the time domain reflectometer and the arc reflection and pulse echo techniques, what we may see is if we're connected onto the source side of the circuit, as I show over here in A, the low voltage waveform would clearly show us the open circuit. And we would take and obtain a measurement to this point. Obviously, the distance measured should be different than the expected or true length of the circuit. This is obviously one of our first indicators that we are looking at an open circuit or a blowout type of a fault, and that we are not actually seeing to the true end of the cable. Now, during the high voltage arc reflection test, when we're sending breakdown voltage to the fault, if the gap is very, very large, we may not get a strong magnitude arc that in essence will drive the impedance to 0 ohms, but the presence of the high voltage, the discharging through the fault, even though the gap is quite large, will lower the impedance some amount. So on the arc reflection, instead of getting the traditional negative reflection that we would normally see during a good strong arc where the impedance drops to 0 ohms, we may actually only see a small decrease in the amplitude of the upward or open reflection that we're seeing from the blowout. Now, this again would be a clue when looking on the time domain reflectometer that, okay, we definitely have a fault. I can definitely make a measurement to the open using just the time domain reflectometer. The fact that when I ran the arc reflection test I got a very small or subtle change is also a clue to me saying thumping conditions may not be very good. I may not be getting very hard thumps, and in essence this may make it difficult for me when it comes time to do pinpointing, because I may not be getting the maximum amount of energy and in essence the maximum amount of sound from the fault. So pinpointing may be a little bit difficult. Again, in a situation like this, option would be to move the equipment to the load side of the circuit and shoot back. On the load side of the circuit, if the gap is more reasonable and we're able to get stronger discharges, what we would see on the low voltage radar is initially the image for the open circuit. We run the arc reflection test, we send a breakdown surge, capture the pattern when the impedance of the cable goes to 0, and we get a nice strong negative reflection. That is giving us an indication that now we're getting a good breakdown. Chances are the audible sound of the fault is going to be much louder, and that pinpointing process is going to be a lot easier. Okay. The next fault that we run across upon occasion is the short circuit or the bolted fault. Now, when I refer to a short circuit in this model, what we're looking at here is a cable that has potentially taken a very high current surge. Rather than the cable blowing apart like we've seen previously in the blowout, what happens here is the insulation resistance gets destroyed, but the conductor comes in contact with the concentric neutral, basically forming just a solid loop of copper and or aluminum. Now, when we test with a standard ohm meter, if we're measuring with a standard multimeter ohm meter, and we're measuring virtually 0 ohms or 200 ohms or less, chances are we will be able to see this type of fault using just the pulse echo technique. Now, the problem when we're using high voltage technique, if we're doing a basic high potential test, we may not detect that we have a bolted fault on the circuit. In essence, what may happen is as we start to try to apply voltage to the short circuit, what we will basically see is the voltmeter will stay at rest. Even for a short period of time, the cable will not sustain any level of voltage because we already have a constant current loop established. So as we try to bring up any potential, all we will see is just a steady rise to leakage current, pure resistive current flowing through the short circuit, and the voltmeter will not sustain any voltage whatsoever. Now, difficulty is when it comes time to do the thumping method. Again, when we go to do the thumping method and we start discharging high voltage surges into a bolted fault or a short circuit, what we're going to see is the meter is going to charge up to the value of voltage that we want to thump at. When the discharge mechanism inside the surge generator or thumper closes, what we're going to see is a strong kick back on the voltmeter and a very strong kick forward on the ammeter. Problem is, acoustically, in order to produce sound, you need an air gap. Okay, as a demonstrator, as long as you have an air gap, you can produce sound. Problem with a bolted fault or a short circuit is there is no gap, there is no discharging or arcing taking place here. So even with a very large, powerful, high energy surge generator thumper, if there's no air gap, we can hit it with all the energy in the world and we're not going to produce sound. So the problem that we face with these bolted faults or these short circuits is we could be walking, looking, and listening for this arcing event to be taking place, and it's not going to happen because what we have is a constant current loop going on. Now, if we were using the pulse echo or time-domain reflectometry techniques, one clue that we would have a bolted fault is when we apply the low voltage of the pulse echo, we actually see the fault without ever applying any high voltage. So this again is a good indicator that what we're dealing with is a very, very low impedance fault, virtually 0 ohms, typically 200 ohms or less. And we see the short circuit or the negative reflection without even applying any type of high voltage to the circuit. Now, the radar is very complementary here because if we were to try to find this fault using just the surge generator and we're not producing any sound, it could be very, very difficult to try to get a pinpoint on this fault. The time-domain reflectometry technique of pulse echo greatly helps us out here because now we can physically see the fault, we can take a measurement to that event, and at least now we have a distance to approximately where this fault has taken place. We still need to work out some type of a pinpointing methodology. In one sense, what we could do is just measure the distance to the fault from both ends of the cable and basically bracket out the actual fault region in order to narrow our search. But again, the pulse echo would definitely assist and aid us in this type of fault where the surge generator all by itself may cause us to waste a tremendous amount of time listening for an acoustic event that simply isn't going to happen. The next fault that we're going to take a look at is what I refer to as a splice failure, a fault that materializes within the cavity of the splice. Now, if you notice my diagram here, I show a very, very large gap. Typically, whenever we're dealing with a fault within a splice, normally the breakdown voltages are going to be quite high. And again, when you think about the way the splice is built, you have a sizable amount of distance between the conductor and the concentric neutral. So it just adds to a little bit of the complication. We have the insulating gels and so forth inside the splice to contend with more material that we're going to have to try to drive enough energy through to get a good strong arc or breakdown at the splice. So again, when looking at this on an average surge generator or thumper, We would charge the internal capacitor to the value that we want to discharge at. At time of discharge, what we may see is a very subtle or weak kick back on the voltmeter and a rather subtle or weak kick forward on the ammeter. Again, that is an indication that we have a large gap. We may also find that the cable fault may not break over on every cycle of the surge generator. Again, that is a good indication that the gap is very large, that we need to actually build or stack voltage on the circuit until we reach a point that we're able to go ahead and break down the excessive gap. So a splice failure can be rather difficult and could require a lot of energy and voltage in order to successfully get it to break down. Now, if we were using the time domain reflectometry techniques, a splice has a very distinctive signature. When we look at a splice on your average pulse echo waveform, what we will typically see is an upward reflection as the radar pulse enters the splice, and then a negative reflection as the radar pulse leaves the splice. So once we start to learn that pattern, we can put these clues together where if we're getting weak thumps, very weak kicks on our ammeter and voltmeter on our thumper during the discharge, that's first clue that we're probably dealing with a large gap. So immediately in our minds we need to process, am I possibly dealing with a blowout or an open conductor type of a fault? Or am I maybe dealing with a fault that's within a termination or within a splice? Now, the radar pattern will definitely help us with the next clue. Do I physically see the traditional pattern for a splice? I see that there's a pattern for a splice. I'm getting a very high voltage breakdown. It may not be breaking down on every thumping cycle. That immediately alerts me that I need to examine and study this splice pattern. So when I run my arc reflection test, I'm actually looking at the profile of that splice, and just like in the blowout fault, I'm delivering energy. It may not be enough to go ahead and cause a full hard arc or drive the impedance at the splice to 0 ohms, but the presence of that high voltage energy surging through the splice will still lower the impedance values at the point of the splice. So again, what I may see is the pattern for the splice simply changes during the high voltage surge, where I get less of an upward and I start to get a deeper negative. That in essence tells me that during the high voltage discharging, I am changing conditions of that splice. I am lowering the impedance. I'm not getting it to where it's driving to a good hard solid arc, but it confirms to me that the breakdown is taking place in that splice. I can make a measurement to that location and then move my pinpointing equipment to that particular location for a more finite pinpoint. Now, another situation that we run across, particularly when we're dealing with unjacketed cables. Now, these unjacketed cables, they may have been put in the ground in the late 1960s, the early 1970s. And the problem that we face here is excessive corrosion buildup and deterioration of the concentric neutrals or the tape shields. Now, these can be potentially dangerous. If we have a fault, an arcing fault on the cable, remember, the purpose of the concentric neutral is to carry the fault current. So if I'm applying a voltage, I get a breakdown, and I have fault current traveling back on the concentric neutral, and if that concentric neutral is severely corroded and or open in locations, that current is going to find its path back to the source. And that path back may be more attractive by traveling on a fence line. It may be more attractive by following the path of a underground water pipe. So caution needs to be taken anytime we're dealing with an open concentric cable, because the potential and the risk of having corroded neutrals is going to grow when we don't have any protective jacketing over the concentric neutral. Now, what we would basically see on the radar system is if we are getting a radar pattern and we are basically measuring a relatively short run of cable, I would expect to be able to clearly see the end of the cable. But if there's a tremendous amount of corrosion, this may attenuate my pulse echo signal, where even on a relatively short piece of cable, I can barely detect or barely get enough energy to reflect off the end of the circuit. This is going to be one of my first clues that, my time domain reflectometer doesn't quite have enough energy to make it all the way to the end and have the reflected image make it all the way back to the time domain reflectometer. What could potentially cause my time domain reflectometer to lose so much signal? Possibly a high resistive circuit. Normally what's going to cause a high resistive circuit is going to be corroded neutrals. So again, we play detective, we start to add up the different clues, and at this point I've tested the cable using just a safe low voltage technique. I know that I very likely have a corroded neutral situation, so I'm going to take the necessary precautions before putting my surge generator into the circuit. Now, if I do run the arc reflection test, I may see a very faint or weak reflection from the fault. If the corrosion is so severe, I may not even see the end of the cable. I may not even be able to detect the fault simply because I cannot get enough pulse echo signal back. Now, the second waveform I show here, if you remember from the cable fault presentation part 1, the technique of impulse current reflection. In impulse current reflection, we're actually using the high voltage surging energy of the thumper to produce the waveform that we're going to analyze and make our measurements to the fault. And basically the pattern that we are receiving or viewing here are the current transients that are caused by the discharging of energy from the surge generator and the discharging or arcing energy from the cable fault. Again, this transient pattern, if we look at any two consecutive peaks, what in essence we're looking at is the surge generator, the fault, surge generator, fault, surge generator, fault. So in this pattern, if we measure between any two consecutive peaks, in essence we're determining the distance between the surge generator and the fault. The reason why this may be a more attractive technique to use when dealing with corroded neutrals is, since I'm using the surge generator to create the signal, I have plenty of voltage and energy if I selected my surge generator properly, that as long as I can get the cable fault to break down, I should be able to go ahead and reasonably capture a transient pattern and make my distance to the fault. Now let's talk a little bit about pinpointing techniques. Probably the most straightforward pinpointing technique, and if many of you have been out doing cable fault locating, you probably have done this technique already, where you apply the surge generator to the faulted cable, begin to send discharge surges every few seconds down the cable line, and in essence you walk along the surface and you listen for the thump, thump, thump sound radiating from the soil. Now, acoustic pinpointing is very straightforward and simple. We can use different type of amplification devices. We can either use the fancy manufactured acoustic devices, and or in some cases we can use something as simple as a parking lot cone. The parking lot cone will shroud any of the background wind noise. It'll also act as an amplifier to strengthen the signal to our ear of the underground thumping activity. Now, the limitation or the potential pitfall of the acoustic technique when used all by itself is acoustic waves, you do have echoes. One is if you have well-established trees in the area of the cable path, the acoustic emission may be traveling, reaches the tree root. Now that wood is going to act as a sound conduit and will actually channel the sound toward the base of the tree. So in this situation, the acoustic signal may sound louder at the base of the tree and not loud over the actual location of the fault. We also have other distractions that may occur in the region of where we're thumping. One of these other distractions may be kids in the neighborhood playing with basketballs. Maybe trucks driving down the road and cars driving down the road causing a lot of background noise. So acoustic, although a relatively straightforward, simple technique, acoustic all by itself could lend itself to some problems. Now, another technique is to use an electromagnetic impulse coil or an electromagnetic detection set. Now, every time the surge generator discharges, it's going to send a traveling wave of energy down the cable. This is going to cause an electromagnetic signal. Now, if we have a electromagnetic pickup set, as long as we are in front of the fault, every time the surge generator discharges, we should get a relatively strong kick in the electromagnetic impulse detector's meter, showing that we're in front of the fault and we still see a significant amount of the surge energy traveling. Now, as we move beyond the fault, the majority of the energy is being discharged through the fault, and the electromagnetic pickup will become weaker and weaker. So a rather crude methodology here. It does a good job of sectionalizing. We can use the electromagnetic detection to sectionalize between cross bonds, for instance on a wind farm application. We can use electromagnetic detection to isolate between two manholes in a network situation. As far as exact pinpointing, not that accurate because we will get a little bit of a carryover of the electromagnetic signal. It will definitely help us narrow down the general vicinity of the fault, but it won't give us a strong pinpoint in most cases. Now, if we combine the two techniques together and we combine the acoustic along with the electromagnetic detection, we in essence get a technique sometimes referred to in the industry as thunder lightning, where the thunder is going to be the electromagnetic surge traveling through the cable produced by the surge generator's discharge. The electromagnetic coil in the receiver will register, show us the intensity of that traveling energy, and once we pick up the electromagnetic signal, in essence we start a timer and we measure the elapsed time to when one of the ground microphones actually picks up the acoustic event. Now, why we refer to this as thunder lightning is if you were ever in a lightning storm, one of the little tricks that they'll teach you is when you hear the thunder count, or my apologies if I got it backwards, when you see the flash of lightning, begin to count until you hear the rumble of the thunder. If the time difference between from when you visually see the lightning to when you hear the thunder, if that time period decreases, it's an indicator that the storm is coming toward you. If the time period between the flash of the lightning and the audible sound of the thunder increases, this is an indication that the storm is moving away from you. Applying these same principles, the lightning is the electromagnetic surge sent by the thumper measured on the electromagnetic impulse detector. Starting the timer, we measure the elapsed time again to when we pick up the acoustic event, or the thunder if you will. And what we're doing is we're looking for the best null in time. Now, if we have two probes, we could actually get a differential measurement, and we will also then at that point know direction. Is the fault closer to this ground microphone? Is the fault closer to this ground microphone? So now we also get a direction of which way we need to move. This is a very good technique whenever we're dealing with locating faults underneath blacktop or concrete. It's also a very good technique if we're trying to locate a fault that's in a conduit where the acoustic signal is going to echo quite large. This will help us track down to the true fault location and not allow us to get fooled or pulled off course due to acoustic echoes. Now, one of the other pinpointing techniques that if we are dealing with a jacketed cable, and for instance maybe we're looking for sheath damage or damage to the outer jacket, Another technique that can be used is the step voltage or the voltage gradient technique. Now here, the way this technique works is we will physically connect a small transmitter. It could be a low frequency AC transmitter. The picture that I show here, the transmitter is actually sending DC surges, sort of a miniaturized thumping system. We connect to the concentric neutral. Now, this will only work if the cable has protective jacketing over the concentric neutral. So we apply current to the concentric neutral. That current is going to travel, and at the hole or breach in the outer jacket, we're going to establish leakage current that's going to travel back through the earth to the ground rod, completing the circuit at our transmitter. Now, our tracking instrument is basically going to be a voltmeter that's polarized, and we are actually going to measure this voltage gradient that's established through the leakage current traveling back to the transmitter and the earth's resistance. Since it is a polarized measurement, if we're in front of the fault, we'll get a positive kick in our meter. If we move beyond the fault, we'll get a reversal in the direction, or a negative kick. When we're directly straddling the fault location, we will see a null in the meter. So again, this technique is commonly used for low voltage circuits, for street light circuits, for low voltage secondary services going to the residents or to the clients. But it can also adapt itself to primary cables, provided that they are jacketed concentric neutrals, by connecting onto the concentric and then applying the current, and then looking for the breach in the outer jacket. That concludes the part 2 of the technical portion of the cable fault locating program. Now, ProTech equipment, why ProTech equipment? Hopefully we were able to demonstrate through this webinar series we do have the technical knowledge to be able to support you if you find yourself in need of cable fault locating equipment and possibly in need of a little bit of application assistance and guidance. We are dedicated to carrying a full line of underground cable fault locating equipment. We carry and stock a full line of surge generators of all voltage and energy classes, the pinpointing equipment, the various time domain reflectometry equipment. We try to provide the best equipment in top condition. We will rent the equipment for as short a time period as 1 day or as long a time period as you require. We do have, sorry my slide is actually outdated here, we actually have 3 locations in the United States. We have Grand Prairie, Texas, we have Chicago, Illinois, and we have Little Ferry, New Jersey, just across the river from Manhattan. So we do have 3 locations that we do warehouse and have inventory in order to reduce the cost of getting these items to job sites. And we do have the technical support. We provide that 24 hours a day, 7 days a week, 365 days a year. And test equipment is our only business. So these are some of the reasons why we encourage you to do business with us. We are here to support you and hopefully make your jobs efficient and effective. Again, I'd like to thank you for your time, for attending Cable Fault Locating Part 2. Hopefully you have already attended Part 1, or possibly after viewing this, maybe have the inspiration to go back and view Part 1. Again, thank you for your time and your support.